like to welcome back Arushi Nath, who was here some time ago, and she'll give us an update on the DART mission on the asteroid Dimorphos, whether NASA successfully moved its orbit or not, and also an update on the Planetary Defense Conference of 2023. Go ahead.
Great, thank you. So hello everyone, my name's Arushi and I'm a grade 8 student from Toronto. It's great to be presenting here in person after so many years. Like the last time I came here was probably 2018 or 2019. And today I'll be talking about planetary defense. In particular, I'll be talking about how I detected the physical properties of asteroid Dimorphos to determine the success of NASA's DART mission, and then afterwards, the briefings about the conference I attended, Planetary Defense Conference. So let me start off by saying asteroid collision risks are real, and they do happen sometimes. Like millions of years ago, the Chicxulub asteroid caused the extinction of dinosaurs. And just a bit more recently, a few months ago in November of 2022, a 1 meter asteroid impacted the Earth, and it actually flew right past Toronto, right past CN Tower, if you got a chance to see it, and it landed harmlessly in Lake Ontario. But this showed that asteroid collision risks are real. And currently, hundreds of near-Earth asteroids keep on being discovered every month, and this is outpacing their analysis by professional astronomers. And this is a big problem because smaller sized asteroids, about 20 to 30 meters, have an impact probability every 50 to 100 years, so we must be prepared for them. And if one of these asteroids were on collision course with the Earth, we would need to know their physical properties like their size, their strength, are they monolithic, are they rubble-based, and if they have a moonlet, to be able to deflect it. And I'm sure lots of you guys heard about the DART mission. So last year in September of 2022, the DART mission, as the first planetary defense test mission, it deflected an asteroid Dimorphos to test this deflection technique, a kinetic impactor. And so today I'll be talking first about an algorithm that I created to measure the effectiveness of this asteroid deflection. And I had three main project goals while making this algorithm. First, I wanted to create the algorithm so that citizen scientists and backyard astronomers can find the physical properties of asteroids using just simple school-level maths and open data. My second objective was to apply my algorithm to the Didymos-Dimorphos binary asteroid system to basically see the physical properties of the Dimorphos and see how they changed after the impact, which brings me to my third goal of measuring the effectiveness of NASA's DART mission. So why did I do this project? Well, first of all, I really love maths and astronomy, and I've been really passionate about these subjects for a long time. Actually, it's RAS that brought me into astronomy, so thank you. And another reason is, as I said, I love maths, and I also love coding, and I've been coding in Python for the last couple of years, so this was also a great opportunity for me to build up my knowledge in this subject. So to observe the Didymos-Dimorphos binary asteroid system, I made use of a node of robotic telescopes located all around the world. And robotic telescopes are simply telescopes which you can control remotely from your home and tell them exactly what part of the sky you want to observe, what filters you want to use, how long do you want exposure time to be, and so on. So this was a great opportunity for me to learn how to create observing plans to observe this asteroid and which were the best days in the month to observe the asteroid based on the phases of the moon. And I think it was a great learning opportunity too. So in whole, I wrote telescope proposals to 4 robotic telescopes in the world in places like Australia, Canada, and Chile. And this gave me over 55 hours of observations of this asteroid. So I took observations spaced into 3 different sections: before the DART impact, during the DART impact, and after the DART impact. So this was a great way for me to measure the baseline physical properties of the asteroid, see how they changed during and after the impact. So now came the fun part, actually creating the algorithm. So the first step to do here was that I had to take my images from the robotic telescopes and find all known stars and known asteroids in my image. So to do this, I made use of open datasets. I used NASA's Gaia database to find known stars, and I used European Space Agency's Gaia database to find known stars, my mistake, and NASA's Horizon database to find known asteroids. So this allowed me to find stars in my image and also pinpoint the exact location of the Didymos asteroid. So now brings me to my second step. Now that I knew where the asteroid was located, I wanted to measure its brightness. And to do so, I created apertures of different sizes around the asteroid. I created an inner aperture to measure the pixel brightness of the asteroid, and I also created an outer annulus. And here the outer annulus was helpful because it allowed me to measure the background brightness in my image. And then I could subtract that from the brightness of the asteroid to get its actual total pixel brightness value. But finding the actual correct aperture size is a pretty hard task, and it must be done really accurately. Because if the aperture size is too small, it will not cover the full brightness of the asteroid. If it's too big, it'll cover too much background noise and might lead to inaccurate results. So I ended up using slope and median functions to find the right aperture size to use. And then I converted pixel brightness into instrument magnitude with a simple log formula. The next step was to find comparison stars in my image. But why would I need to do this? This is because my observations were spaced a very long time, sometimes over 4 hours. And this means that observing conditions such as weather and air mass could and did change. So to account for this, it was very helpful to know that all celestial objects in my image are affected by these scene conditions equally, which meant if I looked at an object in the image with a known brightness, in this case stars, and if I saw how their instrument magnitude changed over time, I could see the effects of weather. And then I could apply these effects to the asteroid's instrument magnitude to get its computed magnitude, which is basically its magnitude without any weather conditions. So for each observation, I selected about 4 to 7 comparison stars, and they had to follow a set of criteria, of course. One thing is they couldn't be variable stars, otherwise their brightness would change, and that would ruin the whole point. Another thing is that their computed magnitude had to be constant over time, and they had to be of similar size to the asteroid. And this is helpful because I was using the same aperture sizes for both the asteroid and the comparison stars, which meant that to make both objects fit nicely, they had to be of similar size. The next step is this wasn't enough to measure just measuring the computed magnitude, because asteroid magnitude can change for several other reasons, especially because of its movement around the sun, because asteroids are always orbiting. So as they orbit, their distance from the sun and the distance from the Earth is changing, which would cause changes in their brightness. So to account for these, I applied offsets to the brightness of the asteroid to assume its brightness was taken as if it was 1 astronomical unit from the Earth, 1 astronomical unit from the Sun, and at a 0 phase angle. So this basically allowed me to get the absolute magnitude of the asteroid over time and allowed me to produce light curves of the asteroid. And these light curves were individual light curves of different nights whose brightness changed only because of the physical properties of the asteroid. So now that I had this, I wanted to find all I could about the asteroids using these light curves. And the first thing to look at is their rotation period. Because asteroids are normally very small, which means they don't have enough gravitational pull to make them spherical. So as they rotate, different sides reflect light differently, causing 2 maximas and 2 minimas in their light curves. And this can be detectable with my algorithm. So I was able to use my algorithm to create composite light curves of the asteroid. So what I did there is basically I combined my individual light curves from different nights to different periodicities. And for each one, as I combined them, I also calculated the root mean square error of my observations from their curve fit. And I was looking for the curve where all my observations would be very close together. So this meant I was looking for the smallest root mean square error. So once I found the light curve with the smallest root mean square error, I knew this was my rotation period. But I was looking at the Didymos binary system, which means it has two asteroids, so I could also look at their mutual orbital period. So to go about this, I first subtracted the rotation period from the main light curve, and then repeated a similar process of finding composites to find the mutual orbital period of Dimorphos. So here we go into results. So I have 7 results. First, I was able to measure the absolute magnitude of the asteroid to be 18.03, and I was able to measure its size to be 820 meters. So I did this simply by looking at the absolute magnitude and then performing some calculations. Second, I looked at the rotation period of Didymos and found it to be 2.26 hours with an amplitude of 0.1. And I found that the rotation period did not change after the impact, but nor was any changes expected. So again, as you can see in these figures here, I was combining my observations to light curves of different periods. You can see 3.4 hours, 4.63 hours, and for each period, I was creating their curve fit and finding the root mean square error of the points from the curve fit. And you can see, if you look at the bottom figure here, you can see the letter D, and that's the smallest root mean square error I was able to find, and that's what gave me the 2.26 hours. So third, I again measured the mutual orbital period of Didymos and Dimorphos before and after the impact. And before the impact, I found their mutual orbital period to be 11 hours and 55 minutes, and it actually reduced by 35 minutes after the impact. So I was able to measure this change in the mutual orbital period. Fourth, I also performed a few other calculations during the impact because so what I did is I looked at the brightness of the asteroid Didymos before and after the impact. And as you can see in the top figure here, every couple of days I was calculating the magnitude and comparing it to the magnitude of the asteroid if there had been no DART impact. And if you can see, right after 26 September, when DART impacted the asteroid, there was a 1.2 magnitude increase in the brightness of the system. And this is actually caused by all of the debris around the asteroid reflecting sunlight. And this debris also led to a 20,000 kilometer long ejecta tail. So to find the ejecta tail, I took observations of the asteroid a few days after the impact and measured the tail length in pixel counts. And after that, knowing the distance from me and the asteroid, I was able to find how long the ejecta tail was in kilometers. So I was also able to find the strength of both asteroids because I did this using both the size of the asteroid as well as rotation period. Because asteroids who rotate very fast with a period that's smaller than 2.26 hours, smaller than 2.2 hours, they must be monolithic. Otherwise, they would fly apart because of such a fast speed. Also, if asteroids are very big, with a size in diameter above 150 meters, they are very likely to be rubble-based, and this is because asteroids are normally impacted by other asteroids, causing them to fragment. So knowing the size of Didymos to be 820 meters, so very big, and knowing the period to be 2.26 hours, I was able to determine that Didymos was rubble-based. And I made similar assumptions for Dimorphos because of 2 main reasons. One is that normally in a binary system, the moonlet is made of the same material as the parent star, parent asteroid. And there was also another reason because if you see back in result 5, I was able to find a 20,000 kilometer long tail coming from the ejecta. And this huge tail length points to the fact that the asteroid had to be rubble-based. So here's the big question. Was the DART mission actually successful in moving Dimorphos? And the answer is yes. Because using the change in the mutual orbital period, I measured a 35-minute decrease after the impact. I applied Kepler's third law, which talks about the relationship between the orbital radius and orbital period of a celestial object. And using this, I saw that Dimorphos' orbit shifted by 40 meters after the impact, so the orbital radius reduced by 40 meters. And this pointed to the success of the DART mission. So for the first time, we have been able to deflect an asteroid as a planetary defense mission. And all of my results were validated by external sources such as NASA, and I received a close to 100% match in most of my results. One thing you might notice is the size is slightly off, 95%, and this is because NASA used the Draco camera, which was on board the DART mission, to get very close-up images of the asteroid to measure its size very accurately, while I simply relied on ground-based telescopes. So we both use different methods here. A few errors and limitations here in my algorithm. So all of my observations from robotic telescopes had a signal-to-noise ratio of at least 100, which means the uncertainty was less than 0.01 mag. And second, when finding the rotation and mutual orbital period, I relied on creating intervals to find the periodicity value, but I was using a simple home. I was using a simple home computer. So of course, I created maybe 5,000 intervals between each periodicity. So if I tried to create more intervals, I would have been able to get more accurate results. But for now, I have it up to 2 significant digits. And I have published my algorithms as open source on GitHub, and I've also shared some of my observations on the asteroid light curve database so that others can also use these. And so on my GitHub, I've divided it into 4 steps training module, which others can replicate by simply adding their images from robotic telescopes and watching the algorithm work. And in addition, after I created my algorithm and tested it, it was great to receive requests from professional astronomers asking me to use my algorithm to analyze binary asteroids, apart from Didymos, where new data has just become available. So this was also a really cool opportunity to test my algorithm and see how well it works, and it was successful. So in conclusion, I was successfully able to create an algorithm to find the physical properties of the asteroids, in particular Dimorphos and Didymos, and apply it in a real-world scenario to measure the effectiveness of DART mission. And my algorithm can be used by citizen scientists and backyard astronomers all around the world to analyze asteroids and speed up the rate of analysis, solving the original problem. In the future, I have several goals for my project. One of them is to expand my project to other missions apart from DART, from places like China and Japan, where they're targeting smaller asteroids, 30-meter asteroids. So it would be great to apply my algorithm there and see what research I can do. In addition, I would also like to expand my algorithm to perform shape modeling on asteroids. So this would involve taking radar observations of the asteroid and perform shape modeling. So now I'd like to step aside and talk about the Planetary Defense Conference. So the Planetary Defense Conference is a conference that's held every 2 years in different places all around the world. And this is a chance for delegates internationally to come together and to talk about the issue of planetary defense. And this was a great opportunity for me. Like, I attended the conference 2 years back in 2021, but unfortunately that was virtual because of the pandemic, so it wasn't the same experience. So this time it was held in Vienna in a United Nations building. So it was a great opportunity coming here in person for the first time. And here I would just like to talk about a few key points that I just saw during the 7-day conference. So I would like to start with the DART mission. And this was a well-awaited session because it marked a very big moment in history. First time we were able to test the kinetic impactor, and it was actually the first session and the first day. So almost the full DART team was present, and their team leads came and talked about various parts of the mission. They talked about their goals and what exactly they were trying to achieve, And the DART mission actually impacted almost near the epicenter of the asteroid, which is where it would get the highest accuracy. So that was pretty great. And they showed exactly where it impacted based on the images from the Draco camera. And also, they talked about the ejecta, which is a really fascinating part because since Dimorphos was rubble-based, as it was impacted, loads of ejecta were crashed out of the asteroid, and this actually increased the momentum transfer efficiency, speeding up the asteroid even more than we had thought. Like the DART team, their original goal was to change the orbital period of the moonlet by at least 78 seconds, and they ended up changing it by 35 minutes. So second is the hypothetical asteroid threat scenario. So what would happen if an asteroid was actually on collision course with the Earth? What measures would we take? How would we deal with this? So during the Planetary Defense Conference, there was a hypothetical scenario where an asteroid were on collision course with the Earth. And this happened during one day. And across the hours of the day, they would reveal new information about the asteroid, about its size, how likely it is to impact the Earth, where would it impact, what type of damages was it likely to cause. And this was also a great opportunity for teams to come together and discuss across the day what measures would be taken, how much knowledge should go to the public, and so on. Third, deflection techniques. This is a really interesting part because if an asteroid were on collision course with the Earth, how would we make sure it is not impacted? How would we deflect it? And I'm going to talk a bit about this later, but I'll just briefly say that techniques can depend on the time. The techniques can depend on the amount of time we have. So if we have a long time before it's going to impact, if we have a short time, and also on the asteroid size. Next up, we have upcoming deflection missions. And this was really interesting because DART mission isn't the only missions that are happening right now. There are several others from countries like Japan and China. One of the interesting ones was the Hayabusa 2 Sharp, which is a mission which is aimed at smaller asteroids, about 30 meters. And there's going to be a flyby. They're going to actually go on an asteroid and rendezvous it to measure its physical properties and also gain more information about it. And this will help us analyze 30-meter asteroids and see what they have in similar. And this is a really important thing to do because it's these 30-meter asteroids, these smaller ones, which have the highest impact probability. Another one was the mission by China, which will do both a flyby and a rendezvous. And this is really interesting because first time they're going to go around an asteroid and take a few images, perform a few tests to get as much information as they can. And then they're heading on to another asteroid to actually land on it and try to take some samples. So fifth, impact and disaster management. So after an asteroid's impacted, how would we deal with this? It's very important to consider that while an asteroid might only impact one specific part of the Earth, the changes that will happen will be seen globally. There will be forest fires, there will be flooding, so many different things could happen. And we have seen here, like there's a forest fire in Quebec, and yet we're seeing it all the way here in Toronto. So you can see that measures need to be taken because global effects will be have. And sixth point, public education and communication. So it was great that this part was also mentioned at the Planetary Defense Conference because normally in some conferences it's left out, but I think this is a really important part. And it's important to get the public excited about astronomy and planetary defense because these are intergenerational issues. And one of the ideas suggested, which I think were really interesting, is if we know the positions of all near-Earth asteroids, maybe instead of making it a huge, like if an asteroid is maybe coming very close to the Earth, we could create outreach events so that people can actually go outside, view this asteroid, and actually have fun while also learning more about planetary defense. So that was a really interesting idea. And this final point is the decision to act. So it's like the politics and the laws. So impacting an asteroid to deflect it isn't really a simple task. What happens if it fails? what happens if one thing to take into account is that if an asteroid, we do not have enough warning time, sometimes we're forced to use nuclear weapons. And while the problem here is that there are several laws which go against using nuclear weapons in space, and nothing that's for nuclear weapons in special scenarios. So it's very hard to get around that. And again, if you fail, you will be in liable issues. So one or two main takeaways is asteroid deflection techniques. So how do we know what technique to use if an asteroid is on collision course? So there are four main scenarios that could happen, both based on how much time we have till the asteroid is going to impact us and their size. So if the asteroid is a smaller asteroid and they're going to impact us very soon, earlier in the next less than 5 years from now, then we definitely do not have time for deflection. And this is because deflection takes a long time. We might impact it slightly, and then over the years, its change will become much more evident. But 5 years really isn't enough time for that, especially because we have to deflect it at least 1 Earth's diameter. So we need enough time to do this. So since in this case you would not have enough time, you would have to rely on nuclear weapons. Similarly, if we have a large asteroid, but still again smaller warnings, you will need to use nuclear weapons. But let's say we have a longer warning time, above five years. Then what we would do is, if the asteroid is smaller in size, then you would rely on several methods you could use actually. One of them is gravitational tractor. So what this is if, okay, great. So one of the methods you could use is a gravitational tractor. This is basically bringing a spacecraft very close to the asteroid to try and slightly use the gravity of the spacecraft to deviate it off course. And eventually, after years, you will see the impact. Another solution is to just use a kinetic impactor, like we've seen in the DART mission. And if the asteroid, we had a still long warning time, but the asteroid was a bigger size, then here we would simply use several kinetic impactors to make sure that the asteroid was properly deflected. One last thing is, this is a small flowchart here, where I've described what we would do in the legalities if an asteroid were on impact course. So first thing to consider is where is it going to land? And does this region or country have a method of deflecting asteroids? And if they do, then that's great. They can go ahead and deflect it. But what if their deflection is not successful? So here the thing happens is if it's completely not successful, it's still going to impact, then this again can have global effects all around the world, which is something that no one wants to happen. And what if it's partially deflected? What if instead of landing in one region, it lands in the other? This will face, this country who launched the deflection mission could face huge liability issues. And this is actually another reason why no one really wants to be the one to launch the deflection technique, because the punishment is so high if it's unsuccessful. Another thing is, if it's successful, then that's great, and the asteroid will not be on course anymore. Apart from the very interesting talks, there was also I also got a chance to talk to several people from all around the world and share my poster with them. And my poster was basically about the same project, measuring the physical properties of asteroids to use it to measure the effectiveness of NASA's DART mission deflection. So here I got to share my research with several members from the DART team, like Andy Rivkins and Christina Thomas. And this was a great opportunity for me to talk to them, especially Christina Thomas, because she's the one who I contacted at the beginning of my project to get advice on observing the asteroid. And in addition, I got the chance to talk to Elizabeth Dotto, who is part of the Hera mission, which will be coming towards the Didymos Dimorphos binary system in 2026 to measure the long-lasting effects of the mission. In addition, I also got to share my poster with people from all around the world who are actually responsible for this planetary defense step. And one of them is Matthew Daniels, who is at the White House. So he's involved in United States deflection techniques. Another one was Lindley Johnson, who is actually the only planetary defense officer at NASA. So it was great to talk to him and actually share my research with him. And finally is Ahmed Shaba, who is the Director General of Nigerian Space Agency. So it was great to see people from all around the globe here, and he actually participated in one of the panels that was held during the event. And so it was great to talk to him and share my research as well. Here comes the fun part, RASC. So of course I had to bring the RASC journal where I got my own publication in it to the conference. And I actually got to meet Paul Chodas, who is a RASC member. And it was great talking to him and about planetary defense and what we've both been doing. So this project, I took it to the Canada-wide Science Fair, and I was able to win the best project award in innovation at the 2023 year's fair. And I actually won the same award in 2022. So this made me the first back-to-back winner in over 33 years. Thank you. So this is the cool plaque that I was able to get. And in addition, I participated and won 5 other awards. And one of the best ones was the Excellence in Astronomy Award from the Royal Astronomical Society of Canada. So thank you, RASC. So I think this was in whole an amazing experience. Like just a bit of background on Canada-wide Science Fair. It started in my local Toronto Science Fair, where I was able to win a gold medal and 2 special awards, including a RAS Special Award. So again, thank you. And this led me to the Canada-wide Science Fair, where I was able to meet so many people over this week-long of fun events, judging, speeches. It was really a great opportunity. It was held in Edmonton, so maybe a bit of forest fires, but still, that was fine. So thank you, everyone.
Oh, thank you very much for a great presentation and amazing feat. Congratulations, really, really well done. Very impressive.
Thank you.
Let's see, do we have some questions in the audience here? Yes, oh, sorry, there you are, okay.
Hi, Arushi. My name's Kathy, and I'm a newbie at astronomy. So I just wanted to say, first of all, that was an incredible project, and your presentation, even as a newbie, I was able to understand a lot of what you were telling us. So thank you for that. Is astronomy in your future, or you're not going to take this and go into finance or something, are you?
Thanks a lot for your encouragement, and definitely, I definitely see astronomy becoming something big in my future. Like I've been interested in astronomy for a long time now, 6 or 7 years, and I hope to keep this interest going forward, maybe study astrophysics or something related to astronomy in the future.
Okay, questions over here?
It's a long time since I've seen you here, so you've grown a bit. What coding method were you using? What language were you using for your code?
I used Python for my full code and made use of like some astronomy libraries like AstroPy, AstroQuery, as well as like some plotting ones like Matplotlib.
Okay, great, thanks.
Hi, Arushi. Great presentation. You are a genius.
Thank you.
Some of the things I don't understand also, but the way you explain, it was so nice, and thank you for a nice explanation. Just a question and curiosity. When you use a nuclear method, what are the risks and what is the legal implications? Like you said, it's less than 5 years. That's the only options, isn't it?
Yeah, that's true. And less than 5 years, you have no option but to use nuclear weapons. And there's several problems that can come up with this. First, when you look at the laws, there are 2 laws that heavily state that to not use nuclear weapons in space. And this is a really big problem because, of course, if an asteroid were on course, you would need to use nuclear weapons. But if, for example, you try and deflect or impact it, and then you're unsuccessful, then we have a nuclear weapon floating around in space, which is something that we definitely do not want to have. So it's definitely a big risk sending a nuclear impactor, and we should only do this if there's no other options left.
Just a follow-up question. So I think we know that radiation is there in space, and nuclear waste might have a radiation, which could be the major risk. So why there is a concern? There is already radiations, there is a high risk of radiation. What other consequences could be?
I think, forget the radiation part, that's definitely a big issue. But another thing is just having something floating in space where we're not sure where it goes, what it impacts, if it causes some other disturbances. And I think, as I said, nuclear weapons are heavily against using them in space. So it would be very hard to get into space, and if it's incorrect, and if it doesn't deflect properly, it'll be very hard to get it off space.
Okay, and we have a question over here.
Hi, my name is Constant, and thank you for sharing your poster and the methodologies behind it. I'm actually curious in regards to the mathematics behind your work, and if you had the opportunity to explore any novel equations that came along to allow you to optimize your algorithm.
That's a great question. And actually, during the whole of my algorithm, I try to limit it to only high school level maths. So this includes maybe logs, mean, standard deviation, mod, and so on. And yes, there are lots of places out there where they use heavily math tools, like for example, for transformation, which I especially tried not to use and instead made my own approach, which used remainder, so modulus, instead. And this is because I would like my results, my algorithm, to be used by people all around the world without any expertise needed on this subject. So I tried to keep it as minimal as possible with the least computational requirements and mathematical requirements possible.
So will you, I understand that you want to be able to broaden your audience and allow people to use it, but on a side project, do you intend on just exploring it furthermore, just for fun, actually?
Yeah, perhaps that could be a good idea, like explore as much as I can, see whatever complex formulas are being used currently. That's definitely an interesting thing to do.
Okay. Do we have any questions online? All right, so here's the microphone for you.
So in order as they've come in, let me read both comments and questions. So the first is from Eric Briggs. Congratulations on winning the Canada-wide Science Fair. Next is from Phil Chow. What you've done is well beyond grade 8 student and teachers. Who did you have as a mentor for your project? I'm absolutely amazed by your work. So impressed.
Thank you. Yeah. While I did not have a specific mentor, I definitely got help from several people, whether it's like from robotic telescopes, which gave me a couple of hours of observation time, or people who just simply gave me advice as I went through my project. But I think like the main thing I tried to do here was self-learning. I also used several online forums if I had a specific query, but mostly it was just looking at tutorials and trying to find my way around things.
Next is from Guy Yanis. I'm not sure if it's just me, but everything I hear Arushi sharing her work, I'm speechless. This is just fantastic, and I agree. Also from Guy, Python is so good. Agreed. And let's see, he also says, there are great modules, libraries in AstroPy indeed. And questions I have, if I may. With Python, was there anything in the higher end of version 3, threads, anything like that that you've used like Python 3.9 specific, or would this work with any Python 3?
This should work with any Python 3. There's nothing specifically to the higher versions I used. I tried to keep it as basic as possible in that way. And actually, I created my whole code in Jupyter Notebooks and just copied it and published it on GitHub. So anyone with Python 3 or higher can use my code.
So I just looked at your Jupyter Notebooks while I was transcribing some of your work, and I was wondering if you'll be putting your slides in a notebook as well.
Perhaps that's actually quite a good idea to put like some figures around. Like I did reach some size limit, which is why I originally didn't put my results that I was getting in the algorithm. But perhaps opening a new one to put all my figures in would be a possible solution.
And one last thing, any chance you'll be putting out an EPUB with more detail as to, I don't like using the word journey, but I'll use it, your journey to get to the end of this project. And next.
Yeah, for my journey, while I don't have much documented yet, I have my project board, which I can share the link later, where I show basically all my steps in a lot of detail. And for the future, while I definitely have a lot of routes that I could take, as I mentioned before, maybe something expanding my algorithm for other space missions or simply to find the shape modeling of asteroids. And I think I definitely want to continue in this route of astronomy in the future.
Things that literally just came to mind for me. Instead of using a nuclear weapon, do your calculations or algorithms ever allow for something like a solar sail that you can project its effectiveness?
Sorry, could you repeat that?
Using a solar sail instead of a nuclear weapon to deflect. Does calculations or algorithms allow for this sort of thing?
Well, my algorithms definitely allow for any sort of thing because you can just add your images, and then you can get the physical properties, and you can repeat this for maybe before impact as well and after impact, and try to measure the physical changes in the physical properties. So my algorithm would work with any deflection technique.
My last question is, using Japanese radar data, do you expect to be a large number of changes in your algorithm? Or do you expect it to be pretty close to what you've already done? Just your best guess.
The radar is going to be used for shape modeling, which is something I haven't done yet. But for the other physical properties, my results were very closely validated and almost 100% accuracy. So I don't think they can be improved by too much.
Thank you.
So unless there are any more questions, I think we'll move on to, first of all, thanks again, Arushi.